Okay, these are going to be our notes on linear approximations. So we start off by asking you a question that we've been asking you pretty much this entire semester. To find the equation of a line tangent to the curve y equals x squared at the point 525. And in order to answer that question, we need the same two things we've always needed. You need a point, which we have at 525, and then you need the slope of that tangent line. And remember, the slope of a tangent line is given by its derivative. So we take the derivative, dy dx, and we get 2x, and that gives us the slope of every tangent line, but we specifically want the slope of the tangent line that has an x-coordinate of 5. So when you plug 5 into this derivative, you end up with 10. So the slope of that tangent line will be 10. And then we just use the point slope of a form of a line. Y minus the y value, which is 25, equals 10, which is the slope, times x minus 5. And when you solve that for y, you get y equals 10x minus 25. So that's the equation of the line tangent to y equals x squared at 525. So once we've taken a look at that, we want to be able to talk about linear approximations. Now what does the slope of a tangent line, or the equation of a tangent line, have to do with a linear approximation? Well, it turns out that when you look at the graph of a curve and its tangent line at a certain point, and you're looking near that point, it gets really difficult to tell the difference between the curve and its tangent line. Let me show you what I mean. If I pull up a graph of those two together, the curve that we just looked at and its tangent line at 525. Here is y equals x squared. This is its tangent line at 525. That is y equals 10x minus 25. This, by the way, is a free graphing calculator that you can find online. It's called Desmos. Feel free to make any use of it that you like. You can graph a lot of things on here. So when we look at this, if we start to look near the point 525, which is where we found the tangent line, as we start to zoom in, you start to have a harder time telling the difference between the blue tangent line and its curve. And as a matter of fact, if you continue to zoom in and you zoom in close enough, even the computer starts to have a very difficult time telling the difference between these two things. So we make use of that when we want to talk about linear approximations. So we use the tangent line at a point, a, f of a, to approximate a function near that point. So in other words, instead of using the function to determine values, we use its tangent line to determine those values instead. And we call that the linear approximation of f at a. And it's represented with f of x equals approximately L of x, which is equal to f of a plus f prime at a times x minus a. Now don't get too wrapped up in the notation. Remember how we found the slope, or excuse me, how we found the equation of that tangent line. We took y minus the y value, which was f of a, equals the slope of that tangent line. Remember, the slope of the tangent line, we took the derivative and we plugged in the x value, which we called a. So that's the slope of our tangent line times x minus the x value, which is a. Now if you solve this for y, what you get is, just add the f of a over, and we'll happen to write that first. F of a plus f prime at a times x minus a. That's exactly what they have here. So this linear approximation or linearization that we're looking at is the equation of the tangent line. The notation just looks a little bit different. So why is it we want to do this? Well, it turns out it's easy to calculate a value, f of a y value, for a linear function. I mean, linear functions are very easy. You just plug in an x value, and at most you're multiplying it times a number and adding or subtracting another number. It's very easy to work with. While it might be very difficult or maybe even impossible to find a function value, that f of a, for the function it approximates. So for example, if you've got a basketball player who releases a ball at a certain angle, how does a small change in the angle affect the distance of that shot? Well, that's actually probably going to be a relatively complicated calculation to find exactly, but if you're willing to approximate it, then it's going to be an easier calculation. Another example is, we know that the cube root of 8 is 2. That's something we already know. The question is, how much larger is the cube root of 8.3? Well, the cube root of 8.3, that's a difficult calculation. So maybe if we could find some kind of linear approximation for it, the calculation would be easier. So here's an example of a linearization problem. This is just the basic. Find the linearization of f of x equals the square root of x at a equals 1. And here's that L of x again. L of x equals, remember this is f of a plus the derivative of f at a times x minus a. So our a happens to be 1. So what this is going to come down to is finding the equation of the tangent line to the function f of x equals the square root of x at a equals 1. To use this form of that formula though, we're going to need f of a, so we'll need f of 1. F of 1 is literally just plugging 1 into your function. It's the square root of 1 for 1. That'll be our f of a. We then need the derivative of this function evaluated at 1. So first I'll take f prime of x, and since our function is x to the 1/2, that's 1/2 x to the negative 1/2, so that the derivative evaluated at 1 is then 1/2 times 1 to the negative 1/2, which is just 1/2. So the slope of that tangent line is going to be 1/2, and then x minus 1 will be in place of this part. So we'll have the linearization as a function of x will be f of a, which is 1, plus the derivative of f at a, which is 1/2, times x minus a. And if you solve that for the linearization, just clean it up a little bit. Well, it's already solved. We'll just clean it up. We get 1/2 x. We get minus 1/2 plus 1, so that will be plus 1/2. This is the linear approximation for the curve f of x equals the square root of x near the place where a equals 1. So in other words, if you were to graph these two, and I'm just going to give a really rough sketch here, if you were to graph these two, what you expect to see is the square root of x looks like this, and let's say this was the place where a equals 1, you would expect 1/2 x plus 1/2 to be tangent to that curve at 1. And if you focus in close enough to 1, you're not going to be able to tell the difference between the line and the curve. So let's use that linearization to approximate the square root of 1.1. So the square root of 1 we know. The square root of 1 is 1. But what is going to be about the square root of 1.1? Now you should know it should be a little bit more than 1. But according to this linearization, it should be about 1/2 times that x value. So times 1.1 plus 1/2. That's our linearization with 1.1 plugged in place of x. So believe it or not, that's not that complicated a calculation to do. I mean, I'll do it up here over on the side. If you take 1.1 times 1/2, remember that's just 0.5. So literally you're going to get the 5 times the 1 gives you 2 5s. You need 2 numbers behind that decimal place. So we get 0.55. So this is literally going to be 0.55 plus 1/2, so plus another 0.5. In other words, it's 1.05. See how easy that calculation is? And it gives you an approximation of about how big the square root of 1.1 will be. Similarly, if we want to use that linearization to approximate the square root of 0.98, the square root of 0.98 should be about equal to 1/2 times 0.98 plus 1/2, which again, it's actually not that complicated a calculation to do by hand. It's just 0.99. Okay? So those are approximations using the linearization. So I've put them into a table. So notice if there's our 1.1 that we just did. The square root of 1.1 we got with our linearization 1.05. Now it turns out if you use a calculator, we're a little bit off. If you put the square root of 1.1 in your calculator, you're going to get 1.0488. In other words, your error, how much you're off, is 0.0012. Notice that is the approximation minus the actual value. And the same thing for the square root of 0.98. The value that we got using linearization was 0.99, and if you put it in the calculator, you're going to get 0.98995 for an error of 0.00005. It's actually not that far off if you're using the linearization. Now, notice I picked a number that's really kind of silly to use, because remember, the linearization is only supposed to be good near an a value of 1. Well, if I use 9, my a value just jumped to 9. That is way too far away from 1 to use. And watch what happens. If you put that in the linearization and take 1/2 times 9 plus 1/2, you're going to get 5. And of course the square root of 9 is not 5, it's 3. Look how much your error jumps. It jumps to 2. So when you're using approximation techniques, what you always want to keep an eye on is, you know your value isn't exactly correct, but how far off are you? And notice, as long as you're staying near 1, you're not that far off. It's when you move far away from 1, that's when you're going to run into problems with your error. Leaving error in this kind of numerical value can be a little misleading. If you tell someone, hey, I'm only off by 1/10, let's say. If you're talking about 1/10 out of 1,000, that's a very small error. But if you're talking about being off by 1/10 and the total was only 2/10 to begin with, that's a large amount of error. So for that reason, we tend to want to talk not just about error, but about relative error and percentage error. So these are the exact same numbers we just had. There's your 1.1 for x, the square root of 1.1, here's our approximation, here's the calculator, and here's the error. So the relative error is given by your error divided by the actual value. So the relative error to this, I literally just took 0.0012 and divided by the 1.0488. I got 0.0011441. And in case that still doesn't give you a good idea as to how far off we are, we talk about percentage error. And percentage error is just relative error times 100. In other words, you take that decimal place and you move it 2 places over to the right. So in other words, if you use the linearization for this approximation, you're only off by 0.11 of a percent, 11/100ths of 1%. That's a really small error. 0.98 is even better. If you use the linearization to approximate the square root of 0.98, your error is only off by 0.005%. That is 5/1000ths of 1%. Whereas if you take a look at x equals 9, we're back to, we knew that was way far off, but look at this. Your relative error goes to 0.6 repeating. I don't know if you can read that. That's a repeating sign over there. It's 2/3. Okay. But so what that means is, look how far off your percentage error is. You're over 66% off from your actual value. That's a large amount of error. So this is a good way to keep an eye on how far off are you. Another question that we want to talk about then, if we're using this to approximate it, if we're going to say, okay, the square root of x, it's about 1/2 x plus 1/2, as long as you're close to 1. But then what if we know we need that error to stay within 0.1? You're not allowed to have error outside of that. This is very common in engineering applications. You're allowed to have error if you're going to approximate something, but you have to limit how much error you have. In this case, it's a limit of 0.1. So if we want to do that, in other words, we want the difference between the actual function and the line we're using to approximate it to be within 0.1 or less than 0.1. So notice I said the difference between them. That leads me to a difference. So that's 1/2 x plus 1/2. The difference between that and the square root of x, I want that to be within or less than 0.1 or 0.1. Now the other thing you got to be careful of is this could be over by 0.1 or under by 0.1. So because it's positive or negative, we need to throw it inside absolute values. Now if you remember though, there's a property of absolute values that if you have the absolute value of x less than a, what that tells you is that x stays in between positive and negative a. So in other words, we have negative 0.1 less than 1/2 x plus 1/2. Sorry about that. So the 1/2 x plus 1/2 minus the square root of x is going to be in between negative 0.1 and positive 0.1. So solving this outright would be extremely challenging because you have an x inside a square root and outside a square root. It's going to get a little complicated. So what we're going to do instead is start off by isolating the line. I'm actually going to add the square root of x to each of the three pieces. Because this is a three-part inequality, I can do that. So we'll have the square root of x minus 0.1 less than 1/2 x plus 1/2 less than the square root of x plus 0.1. And you may not understand why I'm doing that at the moment, but you just need to convince yourself that I can in fact do it using algebra. But the reason I'm going to do that is if you graph the left and the right, notice they both contain square root of x functions, and one of them is getting 0.1 subtracted, and one of them is getting 0.1 added. In other words, those are both vertical shifts. This one is a vertical shift down, this one is a vertical shift up. So graphically what we're going to be looking for is when does the line fall in between these two graphs. Now I've already done that for us. Let's take a look. Okay. Here are the two square root functions. So the red and the blue are your square root functions. And notice because one is shifted down and one is shifted up, they're literally going to form a strip on this graph. And then the green one will be the line. So notice, and I'm going to keep this near x equals 1 because we kind of need to stay in that general area. If we kind of zoom in a little bit, over here, we're going to see the green line outside of the strip, and then it comes into the strip right about there. Now again, Desmos does a good job of telling us what that value is. So starting at an x value of about 0.3056 is when this line is going to fall in between these two values. And it stays inside that strip. It stays in between these two values. It looks like it's almost going to come out here, but it doesn't. If you zoom in, you're going to see the line stays in there. It stays in between these two functions, and then it starts to grow out, and then you're going to see it right about, hang on, I'm going to keep going. There it is. See how it's out over here? Right about there. That is where this is going to come out from inside the strip. So that linear approximation stays within the correct error, or the correct tolerance, up until an x value of 2.0944. So the way that we write that is we say, okay, then this is solved by 0.3056 less than x less than 2.0944. Now you can do that on your TI calculator as well, but that's how we're going to solve this. It's approximate, but it gives us a good idea as to how far away from 1 our x value can be and still be accurate to within 0.1. The other topic in here is going to be differentials. And differentials are one of the things we want to talk about when we examine the curve and its tangent line at a specific point. And what we say about this is we're going to start by assuming y is a function of x. X is your independent variable, y is your dependent variable. For that kind of function, the change in y over change in x should be approximately equal to dy dx for small changes in x. Okay, so let's talk about what that says. The difference between delta y over delta x and dy over dx is that delta y and delta x describe the average rate of change. In other words, they describe the rate of change of the curve between 2 points. And on this particular diagram, that's going to be between P and Q. This goes all the way back to the first things we talked about with these graphs, which was secant lines versus tangent lines. Delta y and delta x describe the average rate of the curve. In other words, it describes the slope of our secant line. whereas dy and dx describe the instantaneous rate of change. Dy and dx, that's the rate of change of the tangent line. Now for small changes in x means you haven't slid q very far away from p. They're still very close to each other. Now I've exaggerated it in this picture because we need to be able to see the difference between everything. But for very small changes in x, so look at the x value for p, it's just x. The x value for q is x plus delta x. They're very close together. Delta x should be very small. So notice that for that change, that's an independent change, it's the same change on the tangent line as it is for the curve. Now under that situation, are dy and delta y going to be the same thing? Notice dy is the change in y for the tangent line, whereas delta y is the change in y for the curve. And they're not the same thing. They should be very close to each other, but they're not the same. And the reason we talk about these when we talk about linear approximations is because this tangent line is our linear approximation as long as you stay close to this point. And what we're saying is the value that you're going to get when you put an input into the function is not the same as the value you're going to get when you plug that same value into the tangent line, but they should be very close to one another. They approximate each other. So when we talk about f prime of x equals dy dx, the differential dy, dx is also a differential, but mostly we'll be talking about dy. The differential dy is literally given by f prime of x times d of x. This dy dx, because it describes a rate of change, it can be broken down into the ratio of two differentials, meaning dy and dx can be separated from each other. It's kind of like if you go back to when you were first learning about slope. I mean, if we tell you the slope of a line is 2/3, 2/3 is the slope of a line, but that's an understanding of you have a vertical change of 2 and a horizontal change of 3. You're able to split those concepts apart. dy and dx work the same way. So the differential dy is found by taking the derivative of f at x times d of x. So usually what we want to do is some kind of comparison. How does the actual value of the function, in other words, that change in y as we change x, compare with the approximated change in the value using the tangent line for that same change in x? So notice no matter which one you're looking at, whether you're looking at the tangent line or whether you're looking at the actual curve, the change in x is the same. So delta x and dx are actually the same if they're the independent variable, but delta y and dy are not. So one of the questions we usually want to ask is compare the two values. Compare delta y to dy. So let's do that for this particular question. We've got a function of x cubed plus x squared minus 2x plus 1, and we're going to let x change from 2 to 2.5. So if you want to calculate first, let's say delta y, go back to the picture. Delta y is going to be this vertical change here. It's the vertical change of the curve. So it is the vertical change between the y value of q and the y value that originated at p. So in other words, delta y is going to be given by the y value that's on top, which is f of x plus delta x, minus the y value underneath it, which is f of x. That is how you calculate delta y. So delta y for us will be f of x plus delta x. That's your original x plus your change in x. That's f of 2.05 minus f of x, which is 2. So that's literally just using the original function. Remember, this is the change in y for the actual curve, not an approximation. So we take 2.05 and we cube it, plus 2.05 squared minus 2 times 2.05, and we add 1. Okay? So you literally throw that into a calculator, and what you end up getting is 0.717625. So that's our delta y. That's our actual value of the curve as you change from one x to another. As you change from x equals 2 to x equals 2.05, the curve changes by 0.717625. So if we instead approximate that change using the dy instead, using the differential. Remember, the differential is f prime of x times dx. In general, that's how we find a differential. Well, f prime of x is the derivative of our function with respect to x. So that's going to be 3x squared plus 2x minus 2. And then we're going to multiply that. That's our f prime of x. We're going to multiply it times dx. Okay? So remember, our x is 2, and our delta x, which is our dx, because they're the independent variable, the change in x is the same, is going to be, we're changing from 2 to 2.05, so that change is 0.05. So in that case, dy is now going to be 3 times 2 squared plus 2 times 2 minus 2, that quantity, times 0.05. Okay, and again, we just put that into our calculator, and we should come up with 0.7. And if you notice, they are not the same. They are, however, extremely close. If you use dy instead of delta y, you're going to be a little bit under your actual value. So let's take a look at this question. We're going to have the radius of a sphere was measured and found to be 21 centimeters with a possible error in measurement of at most 0.05 centimeters. What is the maximum error in using this value of the radius to compute the volume of the sphere? Okay, so before we go through the actual steps, let's talk about the problem itself. So notice we're talking about the radius of a sphere. Keep in mind, a sphere is a three-dimensional object. So unless you plan on cutting that sphere in half and actually measuring out its radius, you're probably going to have some error in the measurement of its radius. So they have found that the error in this is at most 0.05. The other thing you have to keep an eye on is that when you change a linear measurement, which is what a radius is, if you can measure something with a tape measure, it's a linear measurement. Well, if you have an error in your linear measurement and you use that to compute the volume, which is a three-dimensional measurement, the error gets compounded. Think of it this way. Think of it this way. If I give you we'll keep it simpler than a sphere. Let's talk about a square. If I say, okay, I have a square of side 2, then its radius, then its area is then 4, whatever my units are, squared. So let's call them inches. Okay. If I increase that, if I double the length of my side, and I now make that 4 inches, does that in fact double my area? The answer is no. If the side is 4, then the area of this square is 16 square inches. So increasing or decreasing a linear measurement does not affect an area to the same factor. We doubled the side, we quadrupled the area. Now do that again, only this time instead of area, think volume. If you have a cube, this is going to be a really bad drawing, but if you have a cube and its side is 2 inches, then its volume is now 8 cubic inches. If I then increase the side of one of those cubes to 4, its new area is 4 times 4 times 4. It's 64 cubic inches. Okay? It's a huge change. So you've got to be very careful about any error in a linear measurement and using that to compute a larger dimensional quantity, because that error is going to compound over and over again. So that's what this is about. If you've got an error of 0.05 on a 21 centimeter sphere, what is that going to do to the error in your volume? Okay? So we know that the volume of a sphere is 4/3 times pi times r cubed. If you didn't know that, you know it now. We are going to say that the change in that volume for that particular error, it's not exactly going to be equal to dV, but it's approximately equal to dV, as long as it's only a small error. So then we look at dv dr, which is the derivative of v with respect to r. We get 4/3 times pi, that's a constant, so we leave that out of the derivative, times the derivative of r cubed, which is 3r squared. And then those 3's are going to nicely cancel for us, and we're going to get 4 times pi times r squared. So then if we want to approximate the change in the volume for this error, and use dv to make that happen, dv, the differential, is just the derivative with respect to r, so the 4 pi r squared, times that small change in r, times dr, because remember, for small changes in r, delta r should be equal to dr. So we take 4 times pi times that radius squared times the small change in r, which is 0.05. What you're going to get is about 277 cubic centimeters. So for an error in measurement of 0.05 centimeters on a radius, you run the risk of having that volume be off by up to 277 cubic centimeters. That's a huge change. And that's just one of the ways we can use differentials.